Hey Jake, this is lesson 4. Do you know what happened to lesson 3? We skipped it. Good. I combined it. We're going to define electric potential energy. Now first the question we have to ask is, do charged objects have potential energy? Well, we said that a mass had gravitational potential energy because it wanted to fall down. If I had a positive charged earth and this was a negative charge, would it also want to fall down? So does it have potential energy? Yeah. Got a problem though. If this was a positive earth and this was a positive charge, which way would it want to fall? Up. So we're going to have to somehow take that into account as well. But definitely they have potential energy. Or the other way to think about it is, if this is a positive and this is a negative, it would take work to separate them because this negative charge would always be wanting to fall down. Or if this was a positive and this was a positive, it would take work to push them together because the positives want to repel each other. And if I say work, hey, that means there must be energy. Okay? This is going to look very, very similar to the gravitational potential energy. We define potential energy in a manner similar to orbital potential energy. We say that electric potential energy reflects the work that must be done to move a negative charge from a point near the positive charge out to infinity. Okay? So, the amount of work it takes to move and end up at rest that's going to be the potential energy, how much work it takes. Or, if they're like charges, it will be how much work it takes to move them towards each other because they don't want to move towards each other. Recall that the force between charges, much like the force of gravity, is not constant. It varies with distance. And also recall that with the variant force, we can't use force times distance for work. We had to use the area under a force versus distance graph using calculus. You know what? I could walk through the same argument, but you're going to see this. K, Q1, Q2 over R. Where, remember, Jose, potential energy, don't write this down, but potential energy for gravity was big G, big M, little m over R. Negative. No negative here, and the reason there's no negative in the electric potential energy is stuff can fall up and stuff can fall down, so putting the negative is just going to be confusing and redundant. We'll have to decide whether it's negative, positive ourselves, and the way we'll figure it out is going to sort of be along the lines of like and unlike, but we're going to be clever. Okay? But can you see the two equations? Look, the difference is, hey, there's no squared on the R. That turns out to be potential energy for electric point charges. It turns out to be potential energy for mass point masses, for gravitational masses. Now, what we are going to do here is we are going to, do this. We include the plus or minus signs. Signs. Boy, did I type that badly. Unlike forces and fields where we don't put pluses and minuses in, because I didn't define the energy as negative the way we did for gravity, the way we're going to get whether it's positive or negative is we're just going to put the plus and minus signs in for a charge. So if you have opposite charges, you'll have a positive times a negative, which is a positive times a negative, which is a
0.
Positive times a negative, which is a positive times a negative, which is a
negative.
We're going math 8, okay? If we have two like charges, it'll either be positive times positive, which is
Positive.
or negative times negative, which is also in other words, whether you get a positive or a negative work will be determined by the charges. In fact, here's what I remember. Energy is a scalar. For scalars, we include signs. Okay? I'll give you another way to remember this. Forces and fields, forget the signs. Scalars, signs. We're going to include the pluses and minuses. I haven't come up with a better way to remember that, but you need to remember that. So if you want to, you can put a little star next to there. Okay? By this relationship, potential energy is zero at infinite distance. My calculus students, the limit as r approaches infinity will be zero. So you still have no potential energy way out there. When you're far away, there's no attractive or repulsive force, which means you'll float there just fine. By this relationship, unlike charges, a positive times a negative, Colin, is going to give you a?
Negative.
They have negative potential energy because you'll put a positive and a negative into the equation. And this makes sense because it takes work to separate them. They want to fall together. This is the same way that gravity was negative energy because it took work to separate masses. So it's still consistent with our relative to zero at infinity mantra. Really, it's better just to jump on in. Example 1. Says, find the potential energy of a negative 75 microcoulomb charge that is 3 centimeters away from a positive 120 microcoulomb charge. Okay, let's do that first. A. It wants me to find potential energy. Electric potential energy is K, Q1, Q2 over R. And now, we're going to, Jake, have to use our imagination a little bit. This is the charge that's moving, so I want you to just to imagine that this 120 is like thumbtacked to your paper, or in real life, something is holding it in place and not letting it go. And this is being moved by some external agency. I always say, just pretend it's a little invisible angel that's moving it, something off the screen and non-existent, but something is moving it. Or you can imagine that you've grabbed it with your hand. The problem is it's so small and microscopic that it doesn't quite work, but you can imagine you're pulling it and you're feeling it tug back. You're having to do work. Okay? It's going to be K, 9 times 10 to the 9th. Q1, positive 120 times 10 to the negative 6. It is microcoulombs. Again, whenever I see micro, I replace it with 10 to the negative 6. Q2, negative 75 times 10 to the negative 6. Tice, by the way, I put the plus in front of the 120 in our notes just so that you know we thought that you do not have to put a plus in front of a positive number. I'll know it's positive, but just this once I will, Cade. All over, R. Colin, what's R? Don't say 3.
3 centimeters.
Don't say 3.
0.3 meters.
Don't say 30 centimeters. That's 30 centimeters. 0.0. You said 0.3? I think you meant 0.03. How many joules of energy how many joules of potential energy does this negative 75 microcoulomb charge possess? This is once again a good chance for us to practice with our calculators. I got to get this touch screen turned off. Nine times 10 to the 9th times 120 times 10 to the negative 6 times negative 75 times 10 to the negative 6 divided by 0.03, not 0.03 squared. By the way, are you already seeing the potential to get equations mixed up? Have I gone on my rant about it's important to keep up with the homework so you don't, because the classic thing kids do here is they find the force. They put a squared in the bottom, and unfortunately, I would have to give you 0 on the question because you haven't given me anything that I asked for. Do you get negative 2,700 joules? B. Says write a work energy equation if the negative 75 microcoulomb is moved out to infinity. Assume the charges start and end at rest. So we would say work equals change in potential plus change in kinetic. Just like we did, this is very similar to how much work to put a satellite in orbit. What does it say we can assume, Cade? So we can, in this case, assume this. Now, eventually later on, we'll say, hey, what happens if you let it go and it falls? How fast will it be traveling? And then the kinetic energy won't be zero. And in this case, we can. And Cade, what's changing anything? So this is final minus initial. Now, the final is out at infinity. Cade, how much energy do we have out at infinity? We've defined it. 0, because we said relative to 0 at infinity. So this is going to be 0 minus, what was our initial potential energy? It's the answer from part A. Right? I'm going to come back to Colin, and hopefully he's going to redeem himself. Colin, what's a minus minus the same as?
A plus.
So we do get a positive answer because it would take work. This charge does not want to move to the right, does not want to move that way. It would be tugging back at you. You would have to add energy to it. You would have to do work. How much? 2,700 joules. So the signs, if we put them in, our answers take care of themselves. At this location, it is at negative 2,700 joules of potential energy. And the reason is, to get it out to 0, out to infinity, you would have to add plus 2,700 joules. You'd have to do that much work. Was there a C? I think there was. Oh, find the work done by the applied force. Oh, you know what? B was write the work energy equation. C was actually calculate the answer. There. What's the applied force? I don't know, some invisible little angel. Okay. All we're going to do now is show you, similar to what I did with gravity, all the different ways I can now use this potential energy equation. I did write, by this relationship, like charges have positive potential energy. Why? This makes sense because it takes positive work to start out at infinity and push that charge towards that repelling positive. So because it takes positive amount, well, let's just run the numbers. The key idea, we're doing energy. Energy is a scalar. For the scalars, we're going to include signs. You have your formula sheet in front of you. Another dumb way to remember this, Jordan, it turns out, I've told kids this, if you look at the equations for electrostatics, forces and fields on the first line, which is those equations in the first line of electrostatics, forget the signs. There's your 4 F's. Scalar signs. Okay? Example 2 says, find the work required, okay, for an external agent, little invisible angel, to place a positive 2 millicoulomb, milli is going to be 10 to the negative 3 charge, 5 meters from a positive 1.75 millicoulomb charge. Oh, I even wrote there, note, milli equals 0.001. I'm going to go 10 to the negative 3. Assume we're starting an infinite distance away. Again, Jake, in our imagination, we're assuming this one, well, here's the fancy word. We'll say it's fixed. That's our way of saying it's thumbtacked in place. Something's holding it in place. And this one is being moved. Jake, what does example 2 want me to find? Work equals change in potential plus change in kinetic. Look at the picture, Jake. Does it suggest that at the beginning or at the end we have a velocity or a speed? So you know what? If it did, I'd have a half mv squared kicking around somewhere too. I could do it. Jake, what's changing anything? So this is going to be potential energy final minus potential energy initial. Where are we initially? So, how much energy do we have at infinity? This is how we've defined it. Okay. So, I'm just going to get K, Q1, Q2 over, and I guess our final, because it's final. All right. It's going to be K, 9 times 10 to the 9th. Q1, the fixed charge, positive 1.75 times 10 to the negative 3. Again, you don't need to put the plus sign there. I'm just letting you know I included the sign this time. And milli is 10 to the negative 3. What's the charge that we're moving, Jake? How big? 2.5 milli. So positive or negative? Because, are you positive? Okay. Positive 2.5. I'll never get tired of that joke. Times 10 to the negative 3. And then my final distance, Colin, what's my final distance?
5 meters.
Oh, it is in meters. Look at that. See, I gave you a low ball. By the way, I'm going to get a positive answer, which I should, because I am going to have to do work. I am going to have to add energy to get this guy closer. So again, right, as long as you set everything up right, the signs do take care of themselves. It's a little nervous at first. I got negatives. Oh no, I got a minus. It became a plus. Yay! Or I got positives, but they're both positive. Or this would also be the same. Can you also see, adding, if both charges had been negative, they're still repelling, I still get a positive answer because it still does not, they do not want to move towards each other. Again, it's worth practicing your calculator. 9 times 10 to the 9th, 1.75 microcoulombs times 2.5 microcoulombs divided by 5. You're going to find usually for energy, remember for electric field, I said your answers were going to be typically in the thousands, tens of thousands, or hundreds of thousands. Typically, you'll find for energy, for joules, we get answers in the thousands. Is that, you get 7875? So I'll go to 3 sig figs, 7880. Joules. Direction. It's a trick question. It's a trick question. It's a scalar. No direction. Okay? Forces and fields, which are vectors, we forget the signs. We decide the direction for forces by using tie, like, unlike. For electric field by saying, which way would a positive want to move if it could? And we figure that out by using like, unlike. For scalars, put the signs in, no direction. And that's going to be really, really handy because they're scalars. We can deal with angled questions, no trig. Kind of nice. So, key idea. For energy, a scalar, we will include the plus or minus signs, unlike forces and fields, both of which are vectors, where we decide the direction ahead of time. So, my little mantra, forces and fields. Oh, first row, forget signs. There's my F's. Scalars, signs. If you come up with something better, I'll use it. That's what I came up with my students and I a few years ago. But if you come up with a better way to remember it than that, please tell me and I'll use that. Oh, and if we don't have an invisible angel pushing things around, if there's no outside external agent, well then energy will be conserved. We can use conservation of energy. Energy is conserved if there's no outside energy source. Example 3. An electron is originally that far from a proton and at rest. You know what? I would probably underline the word at rest. Which way does that electron want to move? It wants to fall towards the proton. It has potential energy. It's quivering, ready to go. If we let it go, it will fall. And as it falls, as it moves to the left, it'll speed up. How fast will it be going? So, it is released and moves directly towards the proton. Find its speed when it's that far from the proton. Is this question asking how much work? No. But is there a change in height? Yes, it's sideways, but you can use your imagination and just tilt your frame of reference. Is there a change in speed? This is a job for conservation of energy. Now, I used to say, is there a yucky curvy path? Really, what I should have always said is there an inconsistent, non-constant force? Then that's definitely a job for conservation of energy. Because the force changes, it gets bigger the closer you get. Are any of these 0? Are we starting or ending at rest? Yay! Are we starting out at infinity? No. If we were, one of the energies would be 0. I think initial. Okay. Well, let's expand these equations. Potential energy is K Q1 Q2 over, and its initial, R initial. This equals a half mv final squared plus K Q1 Q2 over our final. What are we trying to find here? Jordan. That guy right there. I am not going to get the v by it, so I could. This is yucky. Instead, I'm going to minus this whole term over. I'm going to write it like this. K Q1 Q2 over R initial, take away K Q1 Q2 over R final. That equals a half mv squared. And then what I'm going to do, Cade, I'm going to crunch this whole thing, turn it into a single number. Then, once I have that as a single number, Jose, then I'll go get the v by itself, okay? So we're going to target the left-hand side for quite a while here. K, 9 times 10 to the 9th. Charge 1, it's a proton. Addy, it's a proton.
Really?
Yes. Charge 2, it's an electron, Addy. It's an electron. Nope. Negative, because scalars signs. Which is also why I didn't just replace it with a q squared, right? Because I did that trick earlier in class when we were going through homework. R initial, 2.5 times 10 to the negative 11, pretty close. Minus, hey, Addy, are the K's the same in each? Are the Q1s the same in each? Are the Q2s the same in each? Well then, let's replace them with ditto marks. All over. Our final, 1 times 10 to the negative 11. That equals a half mv final squared. We're going to do the same thing. I'm going to do the first term to like 5 sig figs. I'll do the second expression to 5 sig figs, then I'll add them up, because it's way less typing. Thankfully, though, this is a little nicer than the gravity constants, right? It's a little less typing. 9 times 10 to the 9th, 1.6 times 10 to the negative 19 times negative 1.6 times 10 to the negative 19 divided by 2.5 times 10 to the negative 11. Double check my typing. I think that's right. For the first one, do you get negative 9.216 times 10 to the negative 19? 18? Sorry, 18? Yeah. You know what? I'll write down the whole thing. Negative 9.216 times 10 to the negative 18 minus. And what I really like about this one, Tice, is first of all, I don't need to go in and delete a negative or a change of sign like we had to with the gravity one. In fact, here, all I need to do is in the bottom change the 2.5 to a 1.0. Which you might want to be trying on your calculator. I don't know, just saying. I get negative 2.304 times 10 to the negative 17. That equals a half mv squared. Have I got room still? Oh, good. I do notice a minus minus Kate in the middle, which will become up. But so I'm going to go like this. Negative 9.216 times 10 to the negative 18, take away, answer button. Should work. I'm hoping to get a positive answer, because I'd kind of like to get a positive speed, because it's a scalar. Do I get a positive? Yay, I do. Is that right? 1.3824 times 10 to the negative 17? Yep. 1.3824 times 10 to the negative 17. That equals a half mv squared. V final, but since it's the only V now, I'll even just write V. Robbie, how would I get the V by itself? M and times by? Yep. Oh, and then that gives me a V squared. Okay. 2 times 1.3824 times 10 to the negative 17. Divide by what, did you say, Riley?
M.
Stop. Which M? It's, what's moving? What's moving? It's an electron. I'll bet you the mass of an electron is also on your formula sheet. It is. As is the mass of a proton if I decide to have a proton moving. Isn't it 9.11? Yeah, you just said 9.1. 9.11, right? Times 10 to the negative, sorry? 31. Electrons are small. So on my calculator, I'm going to go 2 times this answer divided by 9.11 times 10 to the negative 31 square root. I like this question. I did it wrong. Oh, after all that, my square root button didn't go. Son of a gun. Okay. Square root of 3.034906696 times 10 to the 13th. Yay. Do you get 5.51 times 10 to the 1, 2, 3, 4, 5, 6? Your numbers, if you used exact numbers, might be different from mine because I just rounded off. You get 5.51 times 10 to the 6? Yeah. Units, it's a speed. Meters per second. Really, this is Physics 11 conservation of energy with Physics 12 equations. But this is the same math as if you drop an object 10 meters, how fast is it going when it hits the ground? It's just I didn't let you hit the ground. I let you get really close. Is that okay?
Fast.
Pardon me?
Fast.
What's the speed of light? I'm glad you said that because this is also a built-in error check. Anybody know what the speed of light is? It's on your formula sheet. Speed 3 times 10 to the 8th. If you get an answer bigger than 10 to the 8th, you're wrong. No, you're not allowed to violate Einstein. Things can't go faster than light. So there's a bit of a built-in error check. In fact, odds are if you get an answer bigger than 10 to the 8th, you probably forgot to square root on your final step. That never happens. Yeah, right. Couple more, we're done. One more, we're done. Example 3 or 4, I forgot to number it. How much potential energy does this charge right here possess? And I can't remember if it was Colin or someone else. One of you was always saying, well, Mr. Dewick, don't I have to take these two into account? No, I'm telling you, ignore how those two are affecting each other. I just want to know how this is affecting this, how this is affecting this. This is going to be, again, our fancy principle of superposition. Let's call this, you know what, since it's a negative 1, let's call this charge 1. It's the charge that we're interested in. You know what, since the right-hand charge is a 2, I'm going to call this charge 2. How clever. Charge 3. Kind of a weird way to label them in terms of an order, but that might help me keep stuff straight easier. What I'm going to do is I'm going to find the potential energy that charge 1 has from charge 3. I'm going to find the potential energy that charge 1 has from charge 2. And then I'm going to add them together. Are there angles here? So how am I going to add them? No. I heard someone say it. What? It's a scalar. What do I care about angles? I'm just going to add them up. No trig. Smile. This is your present. Yeah, no trig. In fact, they used to on the provincial, they would give something like that, charge 1, charge 2, and they would put like charge 3 way out here, and they wouldn't give the angle, and kids would spend hours trying to do some kind of, because you could sort of, they'd give you the distance of 2 and 7, and you can try and kind of maybe figure out, well, no, yeah, no need. No need. I won't do an ugly diagram like, oh, no, you know what, I take that back. You might get an ugly diagram on your test. If it's a scalar, who cares? Okay. It's going to be K Q1 Q3 over R13. If I write a little 13, you guys understand that's between 1 and 3, yeah, for R? It's going to be K Q1 Q2 over R12. Now it's plug and chug, and then, scalar, add them up. Did I say scalar? Signs. One of these might be positive, one of these might be negative. Okay, 9 times 10 to the 9th. Q1, negative 1 microcoulomb. Q3, positive 5 microcoulombs. Colin, what's the distance between charge 1 and charge 3? Please don't say 2.
0.02.
Thank you. We're good now? Yes? I can leave it alone? You'll catch it every time from now on? I've pressed my thumb on the emotional bruise as much as I can. 9 times 10 to the 9th. Next thing you know, I'll start talking about triangles and stuff. Oh, shut up, Mr. Duick. Okay. Negative 6, 5 times 10 to negative 6, divided by 0.02. So the potential energy that charge 1 has due to its location near charge 3 is negative 2.25. Is that right, Mr. Duick? I thought you said the answers were going to usually be in thousands. I lied, I guess. Is that right? Do you get negative 2.25? Okay. Joules? I mean, it's a nice answer. Potential energy between charge 1 and 2, it's going to be 9 times 10 to the 9th. Negative 1 times 10 to the negative 6. Negative 2 times 10 to the negative 6. All divided by, Colin wants me to write 0.04. You know, I think I can kind of backspace and just edit some of this. So it's going to be, insert a negative. A 2 goes there. 0.04 goes there. Positive 0.45? Anyone else double check me? Yeah. I can almost do this in my head now. Certainly no trig. Potential energy, it's going to be negative 2.25 plus positive 0.45. Negative 1.8. What's the negative 1.8 joules telling me? It's telling me that if I wanted to move that negative 1 charge 1 out to infinity, I would have to add energy. In other words, it's telling me if I let charge 1 go, it would fall. If I gotten a positive answer, it would be telling me if I let charge 1 go, it would fall up, which in this case would be that way. It would shoot away from these charges. But with a negative potential energy, it's telling me if I let it go, it will move towards these charges. Now, as soon as it does that, everything's going to change because the charges are at angles, and then because the forces will change. But for now, that's what the significance of the negative is. I'll even put a box around there because we did a lot of work. Okay. How else could I ask this same question? I could ask this same question and get the same answer by saying, how much work would it take to move charge 1 out to infinity? Would be the change in potential. The final potential out at infinity would be what? 0. So it'd just be both initial potential energies. Or, if I started out at infinity, how much work would it take to move charge 1 to its current location? There I'd get a positive answer, I think. Oh, no, never mind. No, I'd get a negative. It wouldn't make sense because it does want to move towards its current location. I would just have to give it a tiny tap and it would fall. So I wouldn't ask that question. What's your homework? First of all, shorter lesson, get caught up on lesson 2. Number 1, don't let the third diagram scare you. It's a scalar. Who cares? By the way, in the third diagram, you're going to get a massive answer because the charges are 1 coulomb, 3 coulombs, and 2 coulombs. Those are massive charges. Again, 1 coulomb would almost certainly cause you to burst into flames, and you would cause your clothing to catch fire. Like the disgusting sci-fi horror movie special effects of getting electrocuted would start to approach there. Okay? 2 is good. 3 is good. I'll skip 4. 5 is good. 6 is good. 6A says find the force. 6B says find the final force. But then 6C says calculate the work. You can't use force times distance because the force is changing. You'll have to find the work by going potential energy final minus potential energy initial plus kinetic. I think kinetic energy is 0. Eight. 3 charges. Yeah. 8A is fair game. Finding the net force from 2 charges. Finding the electric field from 3 charges. That's harder than I'm going to ask you on the test, but I'll throw it in the homework. Again, you'll find the electric field at location X from the first charge. You'll find the electric field at location X from the second charge, magnitude and direction for each of them. You'll find the electric field at location X from the third charge, magnitude and direction, and then you'll add them vectorially. Okay. Got a couple of videos to show you.